Hello everyone. I'll be talking about DNS, though a bit differently than usual DNS talks. I will describe our analysis and reductions to understand the theoretical complexity and power of the domain name system. DNS is essentially the glue that holds internet together by translating domain names like hotnets.hotcrab.com to IP addresses. It is well known that this DNS, the most widely used distributed networking protocol, is complex enough. But we were curious and wanted to know what class of computations can be expressed in DNS. Specifically, we wanted to know whether DNS can recognize regular languages. Alternatively stating that, can DNS simulate an FSM? And is DNS powerful enough to generate the strings in a context-free language? Or is it more powerful like BGP, which is Turing complete? As part of the investigation, we found that the DNS has surprising complexity, a seemingly simple record type DNAME that allows for domain redirection by rewriting the suffix of the input, allows the DNS to recognize arbitrary regular languages. Second, we found, and will show in this talk, that the expressiveness of DNS is beyond that of regular languages. Specifically, the combination of DNAME records and non-determinism due to name server delegation allows DNS to encode both deterministic and non-deterministic pushdown systems and hence to generate strings of arbitrary context-free languages using PDS as a subroutine. Finally, whether DNS is Turing complete or not is still an open question. Okay, this is all good, but why is it important to know all of these reductions? What are the consequences of this expressiveness and complexity? On the positive side, the power of DNS, unlike BGP, can be directly leveraged by the users to build new applications. It presents an avenue to implement filtering, service discovery, or other similar functionality. But the DNS configurations become harder to verify. They will have a time complexity that is at least cubic in the number of DNS entries in the files. And it becomes easier to exploit. With greater power, there will be multiple opportunities to attack the system. Accidental complexity in the system is therefore not a good thing. I'm going to quickly explain how a domain name is resolved in DNS with the help of an example. A user, let's say he's trying to access the UCLA website, he sends the query ucla.edu to a local resolver. The resolver starts by sending the query to one of the root name servers, of which there can be many. Each server will have a file called zone file, which determines how to handle the query. Let us assume the resolver sends the query non-deterministically to the second root server. The root name server does not know the IP address of ucla.edu, but it knows how to reach edu. Basically, what has happened is that the root server has delegated the responsibility of names ending with edu to other name servers, which it returns to the resolver. And this process will repeat. Eventually, the query reaches the server that has the IP address, which it returns to the resolver, which in turn returns to the user, and they're able to reach the web server. The most important takeaways from this slide are that zone files are what determines how a query is processed, and a name server can delegate or refer to multiple name servers, and the resolver can pick any one of them. For the rest of this talk, I'm going to talk about the second reduction, where a DNAME rewriting combined with name server delegation allows the DNS to generate strings of arbitrary context-free grammars. To show that, we first show that DNS can express arbitrary deterministic and non-deterministic pushdown systems and use that reduction as a subroutine to generate strings in the grammar. A pushdown system is a transition system equipped with a finite set of control locations and a stack. It is a quadruple where P is a finite set of control locations. I have also combined an example PDS in the definition, so 1 and 2 are the control locations in our example. Gamma is a finite stack alphabet and ABCD are the stack alphabet in our example. C0 is initial configuration. A configuration is a tuple where the first element is the control location and the second element is the stack in a string format. In our example, the initial configuration has the first control location and the stack has only one element, which is C. Delta is finite set of rules which define how to move from one configuration to another configuration. Transition depends only on the current location and the current topmost element of the stack. The rest of the stack is unchanged and has no influence on the possible next actions. In the result configuration, the control location can be changed and the top of the stack can be replaced with one element as in rule 1 or with multiple elements as in rule 4, or the top element can be popped as in rule 5. There can be more than one rule for the same control location and top of the stack combination, allowing for non-determinism in the system. The slide shows transition between different configurations starting with C0 and with the rules R1 to R5. A different set of configurations will be explored depending on which one of the non-deterministic rules is chosen when there is a choice. An important use of PDS is in representing sequential programs with recursive functions which cannot be modeled using finite state machines. With the help of this same example, I will show how a PDS can be encoded in DNS. The initial configuration is encoded as the query. And the query always encodes the current stack followed by the control location. And the current stack is always encoded from bottom to top and then followed by the control location. Beta is a dummy subdomain to allow DNAME records processing, which I will show in the later slides. The next step is to encode the rules, which is done by creating a zone file called pds.com and place it with the name server server1. Now let us fill in the zone file with these rules. In the pds.com zone, we first encode all the deterministic rules R3, R4 and R5 with DNAME records. The way they are encoded is, for example, if you take rule R4, the LHS part of the rule is encoded in the owner's name of DNAME and the RHS part is encoded in the target field of DNAME. The encoding is same as done with the query. The stack is encoded from bottom to top followed by the control location. For a DNAME rewriting using the R4 DNAME to happen, the query must be a subdomain of C.1. And if it is so, as in our initial query beta.c.1, then the C.1 part is replaced with d.a.1 and everything else before C.1, which is beta here, remains the same. An important property of DNAME is that it will not apply if the query name is just C.1. So we needed to add a dummy subdomain beta. Now, in the same way, let's say if we add DNAME rules for the non-deterministic rules R1 and R2, the zone file will look like this. The problem is that this zone file is invalid and not allowed by DNS semantics, as there has to be only one DNAME for a domain name in the zone. This is to make sure that for a single domain name, only one redirection exists and there is no confusion about which one to follow by the name server. So to solve this challenge, what we do is we leverage the non-determinism inherent in DNS delegation, which is given multiple NS records, which are basically given multiple name server records, DNS resolvers will choose one non-deterministically. So we delegate the A.1 subdomain to two name servers as there are two rules for one A, which are R1 and R2. Next, we then create a zone file for a.1.pds.com at each of the delegated name servers and place a DNAME record for each non-deterministic rule at a unique name server. So we place R1 at server 2 and R2 at server 3. Given this whole delegation setup, if we send starting configuration query to a resolver, then the possible executions of the query correspond exactly to the possible executions of the original PDS. In this way, one can explore reachable configurations of a PDS using DNS. I will next describe how we can use this capability to use DNS to generate strings from any context-free language. Given a context-free grammar, we first create a program variant of it. You can imagine it's like a pseudo code with non-deterministic choices, which when run generate the strings in the language. And as said earlier, PDS are very good to represent programs with recursive functions, and the program version of the grammar fits the criteria and can be represented using a PDS. Then we can use the reduction shown earlier to explore different configurations of a PDS using DNS, and we can generate strings in the context-free language using a trace of query rewrites ending with an empty stack. Please refer to our paper for more details about this. Our work presents an initial investigation into the power and complexity of DNS, and there are several open questions. The most efficient algorithms for PDS reachability, determining whether PDS configuration can be reached in a given PDS, have near cubic complexity in the number of rules. Hence, DNS zone file verification, which requires reasoning about all possible query lookups, also has at least this complexity today. This has not only theoretical implications, but is also a problem for real zone file verifiers like GROOT, which are linear in verification time only in the absence of DNAMEs. So, DNAME has greatly increased the complexity and power of DNS. Therefore, can we design new verification algorithms that scale well with the number of DNAME records for real-world configurations? Next is, can we show that the DNS is even more expressive than a PDS? Or can we reduce DNS to a PDS and show that they are equivalent? Contributors frequently add new drafts and RFCs to DNS specifications with new record types intended to enable new use cases. For example, the recent NAPT record type supports prioritized regular expressions that provide lookup at dynamic resources. How do these newly proposed types affect DNS complexity? And a natural directions to explore is whether the complexity of DNS leads to security implications and new attack vectors. Thank you for listening, and I'm happy to take questions.